All right, I think it's recording. Fingers crossed. Cool. Actually, let me really quick change the layout. All right, it's better. Cool. So you can see my screen, right? Yes. Cool. So welcome to this introduction to Houdini. It's basically, as I said before, it was done for students of different VFX schools, and I changed it slightly. Mainly removed stuff from the beginning to make it also feasible for this one. And what you see here basically is just a preview of what we will be creating. Probably not today, because this is part one, and it's from the course that I did for the school. It was about 8 hours long, so probably we have like 4 sessions for this. Also, it's dependent on the demand, of course. And yeah, the idea is basically to get to know Houdini, some of the workflow principles, show you why it's the best DCC out there, of course. This one is for Julius. And to basically, tell everyone what is proceduralism and why should you care. So let's get started. Cool. So I hope font is big enough so everyone can see it. This is basically the overview. So we'll start with the introduction, goals of this workshop. Then a quick history of Houdini and SideFX. So since when came Houdini into existence, use case overviews, what is it used for? Then I'll do a quick comparison to other DCCs. And then we basically start with the intro to Houdini. So we'll talk about the workflow basics and principles, the UI, just briefly, because this can get quite long. Then context, attributes, different data types, classes. So what are data types? What are data classes? Talk about floats, integer, string, what's a vector, what's a quaternion, what's an array. Where do these particles live? On point, vertex, primitives, or detail. Then some theory. So what's actually a sim? What's a solver? Some hands-on and some theory about it. What roles do forces play in this? What are velocities? Why do we need subframes? All that kind of stuff. Then next would be for each and for each for loops. Some examples, some alternatives, when to use them, when to not use them. The meta import node, time offsets, etc. Then quickly talk about HDA authoring. So that's HDA, it's Houdini Digital Assets. So basically tools that you can export to other DCCs. In this case, we're going to build a quick procedural building. So like a skyscraper generation tool. And then, scatter that or variations of that skyscraper that are basically procedurally spit out by Houdini onto a grid to basically create a nice little city. And then there's also an example of OSM data import. So we'll basically download real-life data from OpenStreetMaps and then basically populate buildings based on that real-life data. Then next would be VOPs and VEX. What's the differences? It's basically the same thing, but different views for it, some examples to go through. And then finally, we go through setups that you saw earlier to tackle basic different effects tasks like Pyro, Pop, Flip, RBD, and Vellum. And then we also talk a little bit, because all of them are rendered through Solaris and Karma, about shading. So binding attributes that are generated, use them in the shader, AOV generation, render settings, and USD in general. And yeah, that's basically it. So again, disclaimer, I hope this won't be too dry. I mean, it's probably not avoidable that parts of it will be dry, especially when talking about maths and attributes and primitives and all that kind of stuff. But I think I kind of designed this course in a way where I thought anything that I would have liked to know back then when I started learning Houdini, I basically wanted to put into this course. So yes, here we go. Don't think there's any questions so far. So goals of this workshop. After this workshop, hopefully you understand Houdini's procedural workflows. What is proceduralism in the first place? Getting a basic understanding of working inside of Houdini. Again, gaining some insight into different kinds of workflows and setups. This is when we basically go through these setups that I showed earlier, and then hands-on work on those setups as well. Maybe I go back to that little preview here again. I kind of picked, this example or basically these setups because they kind of show also the procedural nature of Houdini in the first place, because it's always the same animation. It's like a Mixamo animation that I downloaded from this, breakdancing person. And once you set up one setup, for example, I started with the fluid one, then it's actually quite fast and relatively straightforward to change the source, change the solver, and change the shader when rendering it. And everything else is kind of like the same. So once you have a setup going, it is relatively easy to basically, 80% of the setup stays the same, but you get like vastly different outputs. And then, yeah, you can see the bottom left one. I think I can also zoom in here. I could, yeah, I can zoom. This is one of the other setups, which is covering the for loops and the for each loops, which is basically not a simulation, but basically just, an animation of, flowers opening up and leaves. And this is basically then time offsetted along a curve. So it kind of looks like a simulation, but it actually isn't. Just to show that, not everything has to be a simulation inside of Houdini. And then this is basically the last example with the city generation that can also be exported to Unreal, for example, or Maya even, to create, procedural cities on the fly. Cool. Then you probably know this meme. It's also used for, other stuff, not only 3D software, but yeah, you can see like, I don't know, Cinema 4D, 3ds Max, Maya. The learning curve basically is, it's pretty okay. And the one from Houdini supposedly is very steep, and then people die and stuff. I don't think that's true. I think the learning curve is a bit steeper than other softwares, but at the same time, I think once you got the basic principles and you kind of get them, like, and this revolves mainly around attributes, then I think it's relatively okay to get into Houdini. Because a lot of the times people start, learning Houdini, and then they're like super frustrated because there is quite few tutorials out there that actually cover the very basics. Oftentimes I hear like, yeah, I watched this tutorial and I get everything, and then the guy started to write some VEX code, and I'm like, okay, whatever. And I think this can be avoided, hence this course. Cool, so let's start with the history of Houdini and SideFX. Quick timeline. So Houdini 1.0 was introduced at SIGGRAPH in 1996. And so it's quite old, actually. If you think about it, Maya was born in 1998, more or less. I mean, Power Animator was there before, but so was Prism, which was actually the first name before it became Houdini. And what sets Houdini apart from the other packages out there is it was node-based from the start. And with that, it was also procedural. So Prism or Prisms, that was basically the thing that became Houdini at some point, was actually a set of small tools. Someone wants to enter. Commit. So Prism was actually a set of tools, and some of them were 2D tools, some of them were 3D tools, some of them were, pioneering face morph stuff in like the 90s, 80s. And this is where also the different contexts kind of come from inside of Houdini, because it always has been, not only one context, but more like a set of tools that then basically evolved. As you can see, SideFX is a Canadian company, so I think they're from Montreal or Toronto. I think, if anybody knows, scream, but I think it's Montreal. And okay, thanks, Toronto. Close. And as you can see, it always, was node-based. This kind of looks like VOPs, like a very, very early VOPs, or even, the hypershade in Maya kind of looks like this. And then it, for a very long time, looked like this. And then, I think it's not that long ago when they did like a complete overhaul of the design, and now it kind of looks like, a software that belongs into the 21st century. It was traditionally used for procedural modeling and effects, then lighting, rendering. They were pioneering volumes. Then also compositing, although I have to say, I don't know many people, or I don't know anyone who's seriously using COPS. That's the compositing context inside of Houdini. But recently they were also expanding into also rigging and animation with mainly KineFX. And now with Houdini 20, they also trying to revamp animation with their own animation context, which is using their new infrastructure Apex that's supposedly more going into real time as well. And then also they're expanding, or they're kind of closely connected to Unreal as well, with the Unreal Bridge. So yeah, they also have a bigger game community as well. Then again, SideFX is quite keen on pioneering the implementation of latest industry tools throughout its history. So again, they were the first node-based system. They were among the first creating and rendering volumes as well. Flip fluids they implemented quite early. Then they jumped on OpenVDB. That's the volume format. That's a bit more efficient than Houdini's native volumes. And then also deep rendering, I think, in Houdini 13. And now basically use and they're constantly looking at, what's new, and trying to implement that. I think they are now looking into nano VDBs as well, which is like evolution of the regular VDBs as well. Cool. Then use case overview. So what is Houdini actually used for, and why should you care? It's more or less like a full 3D package. You can do procedural modeling using SOPs, VOPs, and VEX. I think that was one of the first use cases in general for Houdini, where finally you could, procedurally change geometry by swapping out the input, for example. Then animation and rigging by regular keyframe animation, the animation editor, chops, which is the channel operators, and now lately KinEffects as well. Particle effects, of course, it's pretty powerful and art directable to do particle simulations inside of Houdini, and then also other dynamics effects like RBDs, fluids, cloth, wire solver, the finite element solver, vellum, etc. I just want to highlight a little bit out of these solvers here, the finite element solver, because as you know, nothing that we're actually doing is physically correct. Everything is like physically plausible or physically based, but nothing that we do is physically correct. FEM, however, is also not physically correct, but it stands out a little bit because it's it kind of is trying to replicate what happens in in rigid bodies, where it's kind of like simulating how molecules how they create chains and how they bend and when they break and stuff. So FEM is actually also used in some other softwares that are more scientific or like variants from that. But in Houdini, the implementation is not the most stable one, and it's also quite heavy in comparison to Vellum, for example. That's why it's not that much used, but yeah, just wanted to mention it. Then volumes. There's actually two sets of volumes inside of Houdini, the native volumes and then OpenVDB. Difference being that VDB is sparse and the Houdini native volumes are not, which means they basically, if you have, for example, an S curve made out of a volume, right? In OpenVDB, it would really just look at the S itself, where the density is actually present, and everything else where there's density 0, it would completely disregard. So the data footprint is much smaller because you only have voxels where they're needed. And the Houdini native volumes, by default at least, are it's basically like a bounding box. So if you have an S in 3D space, you create a bounding box out of this, and this is completely filled with volume. And then some of them have densities, some of them don't have densities. And this is where the data footprint is much, much bigger than VDB per default. Then grooming, sorry, Mikkel, this should be grooming, is basically, hair, fur, feathers, actually is used quite a lot, especially if you think about stuff like procedurals. So there is, for example, a hair procedural and fur procedural, also feather procedural, which means that you can, the data is generated on render time, or you do your groom on the rest position, on the T-pose, and then you basically, on render time, it gets deformed and simulated and rendered at the same time. So things get very, efficient when rendering with procedurals. Kind of like the opposite of what we're doing. We are basically always trying to get the full groom per frame and render everything, which is quite brute force. Not sure if that's always the case, to be fair, but it has been the case. Then lighting, of course. So I should say traditionally, it's like object level lighting. So as we'll discuss later, there's different contexts, and one of them is the object level. It's basically the highest level, or the lowest level from where you want to see it. There's like basic lighting, like dome lights, grid lights, all the lights that you might know. And then there is this new context called Solaris, which is Lapp's lighting operators, that revolves around USD. And this is what Julius was mentioning before. This was like the katana killer, where they basically wanted to, and kind of succeeded in some ways at least, to rival katana with a complete new lighting context. Then shading, material network, or material library in Solaris now. Then you can also render. There is Mantra. Mantra is, old. It's actually pretty old. But Mantra is super versatile. You can basically render anything in Mantra, and Mantra also doesn't care. Mantra renders everything. In comparison to, for example, Arnold, where, if in Arnold you have one vertex connected to 1,000 other vertices, it just complains and says, "Oh, I can't render this. The geometry isn't clean enough," and it just fails. Same for RenderMan. Sometimes I heard, but Mantra is like a tank. Mantra is, it doesn't care. It just renders everything. It's not the fastest, but it's, it does its job, and you can kind of trust that you can basically render everything with it. And it's comparatively fast rendering volumes as well, in comparison to, for example, Arnold. However, I should say, to be fair, that once it's about pure geometry, Arnold is much, much faster, for example, as Mantra. And then there's the new render engines, Karma, CPU, and XPU, which again are USD-centric renders that were developed for Solaris. So basically, they render pure USD files. Every other renderer, reads the USD, and then it converts it to Mantra, converts it to IFDs. Arnold creates an S file, and then this gets rendered. These Karma or like USD renders are directly reading USDs. So the initialization time is much, much faster because they don't have to do this like internal conversion at all. And again, CPU, because it renders on the CPU, XPU means it can render either on the CPU or the GPU. So it doesn't really matter what where it renders, but it's kind of like two different renders. So they're both Karma, but the code behind it is very different, and they're trying to make the differences disappear. But it's only like, I don't know, 98% there yet. So there are slight differences if you render with CPU or XPU. And then, of course, there's render delegates. This means that if you're using USD inside of Houdini and Material X, for example, then it really doesn't matter, or shouldn't matter, where you render or what engine you're using, because it's all basically unified materials, unified shaders, and unified render environment. So you could render the exact same scene either in Karma or Arnold or Redshift or Octane or what have you, RenderMan. It shouldn't really matter, and it should all look the same, although it doesn't really 100% look the same, because every renderer is a bit different in how it interprets things. It's like if you're shooting with a Canon camera and then a Sony camera, it kind of looks slightly different. And then compositing, again, COPS, the compositing operators. Nobody uses them, to be completely honest, at least not in a production way, I would say. However, I should also say that first, they kind of got a bump recently in usage again when Houdini was releasing height fields. Height fields is basically two-dimensional volumes that are then basically displaced by textures or noises. And this is a very fast and efficient way to create high detail environments like mountains and stuff. And with COPS, you can easily, load in textures, change it on the fly without going through Nuke, for example, and then read that back in and change your height field based on this. So that's the first thing about COPS. So probably they're used now a little bit more than they used to be in the past. But the second thing is that for Houdini 20.5 or 21, SideFX is actually planning on rewriting, or they actually rewrote, it's already in alpha, the COPS and the compositing operators, the context, and completely rewrote it. So basically, it's supposedly a rival for Nuke. Let's see how that goes. But it's at least good that they're looking into speeding up things, and competition is always good. Then plugins and bridges. Before there was Solaris and the render delegates, where you can basically, even with the same UI, switch between renders. There was like the plugins for the renderers, so you could always render in Redshift, Octane, Arnold, H2A. Houdini to Arnold is quite slow, I have to say. This is why we are struggling, and also environment a little bit with rendering stuff in Arnold out of Houdini a little bit. But generally, it's possible. Then the labs tools, which is kind of like a division inside of SideFX that is creating little tools, little HDAs that makes the life of the artist easier. This morning, I was looking at one with Mikkel, where they basically, in Houdini 20, added a couple of tools to import lidars into Houdini and process that quite efficiently. So it's basically a library of little tools that helps the artist and make their life easier, and not make everything from scratch all over again. And then Houdini Engine, as I said before, that's basically if you create these little tools called HDAs and export them to, for example, Maya or Unreal, and then you can basically load that HDA directly into Unreal, and all the parameters that you promoted to, for example, create a city and change the size of each building and stuff, is basically then updated live inside of the DCC. And what's happening under the hood is that while this tool is running, there is actually a Houdini instance running in the background, and that is reading that back and then spits out the geometry. It like generates the geometry and then exports it live to the DCC. And Quixel with megascans, etc., is also available with the bridge. Any questions so far? Nope. Cool. Then off to the next one. Comparison to other DCCs, my favorite slide. So starting with Maya, which is Autodesk owned. Not gonna say anything more. No, it's Maya is the main 3D package still for a lot of studios like Weta, Pixar. Although you should say that what they're using is not doesn't have to do a ton with the original Maya, because What's great about Maya is that, and I don't say this lighthearted, is that it's very modular. So basically the base structure is there, and then you can like put modules on top of it. And Weta and Pixar are basically with a version of working with a version of Maya that doesn't really look like Maya anymore, but under the hood, it's still Maya. And it's traditionally used for animation based on Power Animator, as the name suggests. So it's great to animate. And to be fair, I think also it is quite unrivaled still in animation. There's like new tools also using AI, like Cascadeur and stuff. But so far, the industry is quite slow in adapting these things. And I think it just like is such a enormous user base that it will probably never go away. Although the core is from the 80s. So it's like, yeah, it's like a little dinosaur. In parts, there is procedural workflows, but they're also quite limited. So again, if you think about the history, I think it's called in Maya, where you can basically go back and change. When I started doing Maya, I also worked with Maya quite a long time in university. I remember like the tutor telling us, look, I can create a sphere, and now I select faces and I extrude them, and now I can go back in the history and change stuff. And then everything completely broke, and the sphere became like a cube. And it was like, yeah, maybe that's a bad example, but this is how like proceduralism works. So yes, in parts, but nothing in comparison to, let's say, Houdini, for example. And it's more like a layer-based workflow, not so much node-based, although there are some parts that are node-based as well, like the hypershade, etc. So yeah, so far to Maya, I would say. 3ds Max is now also Autodesk owned. I think they bought it in 2012 or something. I don't know, don't remember. But 3ds Max, when the cycle, so whenever a new version came out, it had a bunch of new features, which was great. And then Autodesk bought it, and then it kind of stalled. And now we have area shadows in the viewport, and it's like it became very incremental the moment Autodesk bought it. And it's quite similar to Maya, I would say, but more focused also on effects. There was a lot of effects done in 3ds Max as well. Before people were jumping onto Houdini, I think Pixelmondo was doing a lot, for example, in 3ds Max. Also Scanline, I still think they're doing it in parts of their software, at least in their pipeline. And there was a great plugin, I think it was called Fume Effects, where you could do quite a lot of effects on it, and thinking particles as well. And it also had like limited procedural workflows. So all of the softwares kind of have like procedural abilities, but comparably limited. Then Blender. Blender is open source, which is great. Because everybody can kind of contribute to it. It has like an enormous user base as well. It recently became very powerful with its procedural workflows, mainly the geometry nodes, which is gives Houdini a run for its money if it's coupled with the very quick render engines as well, being Cycles and Ivy, Eevee. I never know. Ivy or Eevee is basically the viewport render. It's almost like a game engine, and Cycles is the offline renderer, but both of them are extremely fast. And that was always the thing where Houdini was a bit behind with just Mantra, where you can do all these procedural things, but then it renders forever. And this recently changed with Solaris and Karma. But still, if you compare, especially Eevee to something like Karma XPU even, it's still much faster, and it's really great. Like, I think if I would have to learn any new software next to Houdini and Unreal, it probably right now would be Blender. And then last but not least, Cinema 4D. It's Maxent-owned. It's German. It has procedural workflows, kind of comparable with Houdini in parts, but also more limited. Mainly the MoGraph module they have. And the good thing is it's very intuitive and user-friendly, but not really for feature film work. It's more like for commercials and motion graphics. But it's a great software to learn 3D in the first place. I started also with Cinema 4D back then when I was 15. So yeah, that's there's more, of course. There's more DCCs out there, but this is basically the overview. Any questions so far? No? Cool. Then let's start with the actual intro. So yeah, I'll start with the UI. Again, not too extensive because Houdini has a lot of contexts, a lot of menus. So this will be quite, just as an overview. We'll go through the views, so the scene view, network view, parameter, inspector, render view, etc. Quickly talk about shelf tools. Then look at the contexts. So that's the famous sop, stop, swap, shops, cops, tops, lops, robs, shops. Glad that's out of the way now. Which always means just something and then operators, right? So SOPs just means surface operators because you're working on the surface of a geometry. DOPs means dynamic operators because you're working in simulations. In the simulation context, VOPs means VEX operators. That's the original shader language. CHOPs, which is the channel operators for procedural noise, curves, keyframes, whatever. COPs, compositing operators. TOPs, task operators. LOPs, lighting operators. ROPs, rendering operators, and SHOPs, shading operators. Great. Now that we have this out of the way, I'm going to show you all of them after this slide. But I think what's the most overlooked and most important basic thing is attributes, and that there is like attribute classes, and then there is attribute types. And attribute classes are basically where does the attribute live? Does it live on points? Does it live in vertices? Does it live on primitive or on the detail? And to maybe show this a little bit better is this little visualization, which I found quite helpful. So the whole thing, the whole face in Houdini is called primitive. And you can say polygon, you can say face, you can say that's all like primitive in Houdini. And this is basically made out of 4 points, right? 0, 1, 2, 3. Computer graphics, you always start from 0 to count. So 4 points describe this primitive, this face, this polygon. And then in between, on each corner, basically, of each point to the next point, there is this vertex. So you have, in this case, you have 2 vertexes here, you have 2 vertexes here, and you have 1 vertex here, because there is no neighbor here. If this would be a mesh, then each of this would have basically 4 vertices. And it's always a bit weird to explain, but vertices basically describe the gradient of a primitive. So that's why normals normally live on vertex level, and UVs as well, because they basically describe thank you. They normally describe the the surface of each primitive, and therefore points are not enough, but you need really as you can see here, 3 vertices to describe the gradient. I hope that makes sense. Then there is, and an attribute can live on each of them. It can live on primitive level, point level, vertex level, or detail level. Detail level is basically if you have a whole mesh and it has like a lot of primitives, it's just the whole mesh is considered a detail, which means there is one attribute that can stand for, I don't know, Monica, for example. Monica would be a digidouble on grow, for example. That would be a detail attribute, but you'll see that when we talk about this inside of Houdini. Then each of those attributes can be of a different type. So there, for example, is a float. Attributes can be float attributes. That means it's just a number which allows decimal values. And it can be positive, can be negative. It can also be like 0.0. So 1.0 is not an integer. It's still a float because it has a comma or a point, because it allows decimals. Then an attribute can also be an integer, which means it's just a number without any decimals. And again, it can be positive, can be negative, can be 0. Then an attribute can be a string, which is just a text. It's non-numerical values. So often reference paths or names or USD paths are basically strings. And yeah, this is a good example. Even this is a string, right? Text is basically just a string, but mainly it's used for also name attributes, for example, in RBD sims. And then there is vectors. And a vector is like a classic vector would be a 3 numerical vector, which means it has 3 values, RGB, X, Y, Z, whatever you want to call it. There's also 2D vectors and 4D vectors. It's always a bit hard to describe, but I have actually a delicious description for a 4-dimensional vector. And that is, so a 4-dimensional vector is, for example, quaternion. And the quaternion is basically, so vector, right? A vector is, if you remember in math from school, basically, you have 3 values and they describe this arrow in space. And if you go to the Christmas market and you buy, one of those fruits that are covered in chocolate, they come on a stick, so your hand doesn't get like all chocolatey. And if you imagine you go there and you buy a banana, a very straight banana, then that's your vector, right? That's your vector in 3D space. And the 4th vector would be basically the stick. So depending on where the stick sticks in the banana, and then you rotate the stick, it describes the rotational vector of that vector. So it's a 4-dimensional vector. So it sounds cooler than what it is. It's just a vector with another attribute on top that describes something. In quaternions, it's used for describing the rotational value and the vector of the rotation, basically where it rotates. I hope that kind of makes sense. Cool. So this is basically mostly what you need to know about the basics of attributes. Again, we'll take a look in a second inside of Houdini, how they look like. And then later, we're going to also, talk about Vex, which was originally a shader language inside of Houdini. That then at some point they realized, hey, we can also, plug this into geometry and, do geometry manipulation with it. And VOPS is basically the exact same because it's a VEX operator. It's just a node-based UI for it. And there is advantages and disadvantages, mainly that VEX is multi-threaded and VOPS isn't, so VOPS is generally slower. But it's more user-friendly for non-coding people. And then last but not least, we're going through the examples, which probably takes the most of the time. And yeah, again, this is the overview of those examples. Cool. Any questions so far? Nope. Cool. Cool. So let's talk about Houdini, the UI. Again, I'm gonna just do it very, very quick and basic because this otherwise takes quite a lot of time. So if you open up Houdini for the very first time, you can see that the viewport is pretty big here. You have your parameter view up here, and you have your network view over here. So if you create a geometry on object level, you can see here on the bottom right, it says objects. That's object level. So this is where I previously said, all the lights live, all the cameras live, all the low-level stuff gets created. And then inside of the geometry context, if we double-click, we can go inside. There is, we can create a sphere and a box and basically any geometry or surface. So that's SOPs, surface operators. And that's why this says geometry here. So again, if we go up, object level, now geometry level. And if we go, for example, into a VOP network, point VOP, it says VEX context, because now we are in the, we went from low level to very high level to basically, here in this context, we can change position, velocities, force, age, color, all these kind of attributes. Cool. So network view, parameter view, again, it's context sensitive. So whatever I have selected here changes the parameter view over here. Then I just start from the top. Here you basically, have from any other DCC as well, like new, open, save, merge, to merge other Houdini files inside of this session, import for object, OBJs, FBX, Alembics, etc. Export, same thing. Edit, same thing as already. Cut, copy, paste, preferences, hotkeys, which is quite interesting because you can hotkey anything and make your life easier. Aliases and variables also live in the preferences section of the edit. We're going to talk about aliases and variables on a later point, but they're quite important as well. Then render is, again, Mantra is the old one, Karma is the new one. There's a couple of render views. There is a scheduler if you render stuff offline or in the background. Then you have this little scheduler where you see all your jobs basically running in the background on your local CPU or GPU. Then assets, this is mainly for, asset manager, digital assets, the tools that I previously said you can export also to other DCCs, or you can, make a little library and, reuse stuff, because the power of Houdini, again, is that you don't always start from scratch, but you build tools, you save them, and then you reuse these tools over and over again. Windows, it's just all the different monitors, code viewers. Yeah, it's a bunch of windows that you can open. Labs is the library of tools, so you can update this library, or you can download it, or you can go to the quick tips and see random quick tips of whatever it's like quick tips for Houdini in general, I think. Then the help section is quite important because there's like the start here thing that, if you have a connection to the internet, then, it opens up this tutorial section, getting started. There's like learning path, there's tutorials, there's HIP files that you can download and look at. This together with the example files, for example, is super helpful to get started with Houdini and learn by just looking at stuff. I should also say that whatever node you're looking at, let's maybe bring up some labs node, whatever. There is this little question mark here at the very top, where you can basically, on every node, there is like this little question mark. So you can just click on it, and that will basically open up the documentation and bring you to exactly that tool and what it does, basically. So in this case, it creates fancy sci-fi panels. And all the parameters are explained, and in some cases there is also even examples. So example files that you can open. Probably not for the sphere sub or the box sub, but you get the idea. There is an example for the sphere, which is great. So you can load it or launch it, and that will load the example files. Cool. Then, so that's the help section. Then this one is just a layout thing. So you can, create your own layouts and save them. This one is the build one, so the default one. I highly recommend to, change this. Mine is called my initials because I like to have more than one network view. So I always have like two, and they can be separated from each other. So I can be in two contexts at the same time and then reference stuff from one to the other. And I also like to have the geometry spreadsheet open at all times, which again shows all the all the attributes and where they live. So again, what we discussed earlier: points, vertices, primitive, and detail. But we're going to talk about this a bit later. So you can do your own by, if we're getting back to build, you can go to these little triangles here and say, for example, split pane bottom top. So now I have two, and now I can go to this little plus and say, I want to have an inspector, for example, geometry spreadsheet. And now I change the layout, and now I can save it. So I can go to save current desktop. So that will overwrite my standard build setup. Or I can say save current desktop as and call that test. And then it's going to be saved as test. So you can, you can also say make the current desktop default. So whenever you open up Houdini, it's defaulting to your specific custom layout, which in my case is this one. Great. Then not going to talk too much about these guys here, because these guys are mainly presets. And I don't know many people who actually use them. I certainly don't. You can create the box by just clicking here and then clicking somewhere, and this creates, as you might expect, the box. However, I can also just like in the network view, press tab or right click and type box. And that creates also a box and a sphere and a tube and the torus. And basically everything that you see here, you can, it's much more straightforward than typing it here, dropping it here, than, looking it up in one of those tabs. Same goes for, extrusion deformers. Like these are just nodes that can be basically dropped directly in the network view. Excuse me. And then same goes to the shelf tool here on the right. So these are mainly presets. So again, I can press camera, and this will create a camera. That's actually the only one where I think this is actually useful. I kind of use this all the time because if you press on that button, it will create the camera on your current view where you are in the scene. So if I'm looking at, my grid here, and I create the camera, and if I dive out, it created the camera directly where it was before in the viewport. So that's quite handy. If I drop a regular camera, it actually is in the origin. So I hardly never use any shelf tools, but for camera and lights, because for lights it's actually the same. If I know that my camera is, I don't know, here, and I want to add the light that comes from the back, for example, I can control click on that light, and it will create a light where my current view in Houdini is. And it's also locked per default. You can see this by this little lock indicating that I'm looking through the point light. And I can unlock this by, clicking on this little lock here. And now I can see that the point light that then I can change to, I don't know, direct light or sunlight, is in that position where previously my camera was looking at. Other than that, it's really like presets again. You can, even if you go to Pyro, you can click on sparse fireball, and you can click somewhere, and then it will create a fireball right there. Maybe I shouldn't show this, because then it's going to be like, why is the bidding days for an explosion so high? But yeah, generally, actually, I don't know why this looks so shitty now. Because the shelf tools are actually quite good, a good starting point for also junior artists mainly. So again, if I click play here, you can see there is an explosion. And again, it looks very crappy. Not really sure why, but yeah. Anyways, if you render it, it doesn't look as crappy. And if it basically, again, is a preset, so it creates, that's the source. And then this is the simulation. And it gets you a starting point. But to be honest, you can also do this directly in SOPs. So if you type in Pyro configure something, fireball, it kind of creates a preset as well. And you can directly look at it in the viewport. So again, it's normally, as a junior artist, it's great to use them, the shelf tools, to figure stuff out, how it works, but you tend to not really use them in production that much, because to be completely honest, some of the stuff is also not very efficient sometimes, or it just like is very limited in what it's doing. So that's why you do a lot of things just manually, because it's fast. It takes a bit longer in the first place, but then it's much more controllable and easier to handle along the way. Cool. So this is the shelf tools. Then we have all the viewport stuff. So about the viewport, maybe if you press D for display options. You can, change, for example, the background to, light or dark or gray, or change the geometry visualization as well. So, for example, if you have, let's say, if you have points in the viewport, and they're quite small, you can change the visualization stuff and change the point size. This doesn't tweak any attribute. This is really just a pure visualization thing. If you render this, it will always look the same. It's really just a viewport thing. But what I actually wanted to just say and show is that as from other DCCs, also Nuke, this is context sensitive. So if my mouse is over the viewport and I press D, then all the display options for the viewport come up. If I do this over the network editor, then it creates this display options for the network view, as it says here in the description. And same goes for anything else. It's like pressing S in Nuke while you're in the network view or over the parameter view. Great. Then, I mean, all these gizmos, I don't think I have to go through them. It's basically, what do I want to work on? Do I want to work on the points, the primitives, the vertices, the edges? So if I select points, then as you might expect, I can manipulate points. If I go to the edges, I can select edges and manipulate them. And same goes for primitives and vertices. And actually here, as we discussed before, the blue dot in the middle, I hope you can see it, is basically the point. And then we have the 3 vertices around it, describing basically the gradient of the primitive. So this guy goes from here, this guy goes there, and this guy goes there. Yes, just to recap on that one. And I mean, yeah, again, it's translation, rotation, and scale. Scaling points, this doesn't make a lot of sense, but you get the idea. And then there is like this multi-tool, which basically lets you allow to work on anything. So if I look at this, for example, and I have this multi-tool selected, then I can rotate, scale, and translate at the same time, because all the gizmos are there at the same time. This is also important when, for example, painting on geometry. So if we would subdivide this cube, or generally give it just more divisions, and I would, I don't know, paint a color. In this case, it's a CD attribute, so it's a vector, R, G, and B. Then this would basically work, let's pick some color, on this multi-tool, or this show handle tool, whatever it's called. And, if I don't add this, I don't have a color attribute. I purely have a position attribute, and it lives on the point. I also have some vertices, as we've seen before, and I don't have a primitive attribute, and I don't have detail attribute. But the moment I paint something on this, then I get CDR-GB, so a vector. And depending on the color, that changes as well. Cool. So this is, but again, we're going to talk about all this and attributes in detail later. We are still on the UI. Then here, Flipbook is basically the Play Blast bonbon. So whenever you want to do like a Play Blast to show something really quick in reviews, then you can generate a Flipbook and without rendering anything directly from the viewport. And then it looks like this. And then the same goes for Mantra. You can basically do like a Mantra Flipbook, but that would be very expensive because it would happen locally on your machine. I have to be a bit careful about the time because, as I said, like viewport or UI explanation is always a bit, can go quite long. Just quickly, here, sorry, this is the world grid, which is kind of important in Houdini because Houdini works in meters instead of centimeters. So Maya, for example, or most of the other DCCs are working in centimeters, which means 1 unit is 1 centimeter. In Houdini, however, 1 unit is 1 meter, which means that if I create a box, and I look at it, I can see that the size is 1, 1, 1. So it's 1 meter to 1 meter to 1 meter. And you can also see this here. So since it's, in the middle, right in the origin, it's like 0.5 meter here, 0.5 meter here, 0.5 meter here. And that's quite important because all the simulation, all the parameters, all the noises that you by default add to your simulation or to your object are kind of tailored to that world space. So if I would, I don't know, have like a rigid body simulation of a building collapsing, and the building is actually not like 20 by 10 meters or something, but it would be 10 centimeters, then the dynamics would completely look off because, gravity, everything, that's all the forces, they're basically tailored to that world space. So it's quite important to keep the Houdini scale consistent. So what we do actually most of the time is we import the geometry that comes from the upstream departments, from Maya, for example, as an animation. And then first thing we do is we scale that down to 0.1 of what it was before to get it back into the Houdini scale. Because if we wouldn't do that, then everything that is set as a default parameter, for example, noises, and as I said, like all the dynamics parameters are 10 times too big. And then once we are ready with the geometry manipulation and we want to export it, we basically scale it up 10 times back. So, the new geometry that we created or modified is then again in Maya scale and gets passed to the next department. Cool. Then, this is basically just viewport visualizations. This is no lighting. This is basic lighting. This is normal lighting, which basically means that it will take into consideration the lights in the scene, but without shadows. And then high quality lighting is basically saying, I am taking still no shadows. And this one is basically the one that's most expensive, but also, looks the best. However, this is OpenGL, and OpenGL is quite old and quite buggy sometimes as well. Oftentimes in Houdini, you see stuff in the viewport that shouldn't be there. And then you're like, oh man, why doesn't this work? Why do I still see this? It's not even highlighted anymore, right? And what you then have to do is press Control-T to create a new instance of the scene view. Or you can just like go here and create a new scene view to reset basically the viewport. Because sometimes it just gets stuck and then you see geometry that you shouldn't see. And this Every Houdini artist knows about this, and it's super annoying because it makes you question what you've done. And then you realize, oh shit, it's the viewport, and then you just do a new one, and then yeah, okay, it works now. And recently, they're with Houdini 20, they're basically creating their own viewport, which is based on Vulkan, and that's basically the pendant to the Ivy viewport renderer from Blender. That it kind of looks like in the viewport. The viewport in Houdini 21 supposedly will look much better, almost like a rendering, because it's more like its own game engine view. So Playblast will look much better probably. Cool. Then again, there is a bunch of inspectors, viewers. I'm not going to go through all of them. The most important ones are the ones that you see here: the geometry spreadsheet, the scene viewer, the network view, and the parameter over here. Then down here, there's a timeline. So quick word about the timeline. If if we have a simulation and we press play, then you see this blue bar, which basically indicates this is cached in a temp cache, basically on your RAM on your local machine. And if I go back, the cache is still there, which is tricky because sometimes you change stuff. I don't know, increase the velocity ×2, and then this turns orange, and it still plays back. So you might think in the beginning, well, I changed the velocity. Why is my simulation looking still the same? You have to actually go back, and then this bar disappears. And if you press play again, then you can actually see what you're doing and what you changed. There's also like a shortcut for this, which is Control Up to go back, and then actually this should because I didn't change anything. But yeah, if I would change anything and I go back, then yeah, it does work. So timeline, again, you can do keyframes, very basic. Let's create some keyframes. So to create a keyframe inside of Houdini, you can, on whichever parameter you want to animate, for example, the position in Y, you can just like Alt-click to create a keyframe. That's indicated by this little green thingy down here. And then if we, animate it, we do another keyframe, and then we do another keyframe, and yeah, another keyframe. So keyframe animation is great. And now we have like this bong bong. And you can even, select keyframes, transform them, change them on the fly, delete them as well. And if you want to go into detail, you go to the animation editor, and you can basically see the curve interpolation. You can change it to be, linear, for example, or to be Bezier, or play around with the tangents. So yeah, that's basically the very basics of keyframe animation. Then you have this, this is actually quite important, the real-time toggle. So sometimes, for example, on easy simulations that are not computational, very heavy, Houdini is quicker than real-time. So it also displays it quicker than real-time. It just displays it how fast it can possibly display it. So whenever you're working on anything, it's actually good to press this little real-time toggle, which basically sets everything to 24 frames. So you can actually watch it in real time rather than being super erratic. Then the global animation options are also quite important, because here you set basically your start and end frame. Of course, in our production environment, we don't need to do this because this is all set by pipeline. However, we talked about integer and float before, right? So decimals versus non-decimals. And by default, this is set to integer frame values, so I only see full frames, right? I only see frame 48, 50, 85, 86, 87. However, I can uncheck this, and now I basically see substeps, so 0.1. And if I now skip to the pipeline, to the timeline, I can see that I'm skipping in steps of 10. So basically, now I'm in subframe 86.1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have basically 10 subframes. Why this is important, especially for simulations, we'll discuss when we talk about simulations. But yeah, just wanted to mention it because it's quite important as well. Any questions so far from anyone? Then I would say, UI. No, actually, let's talk about the context first. So object context, you know already, right? Then SOPs context, you kind of know already as well. This is where we modify geometry. Then we already also talked about OpX context, which basically lets you manipulate the very detail intrinsics of a geometry, like velocities, force, normals, add noises to everything. So very, very detailed level. Then we have the channel operators, chops context, which again, if you create, I think I have to do this here. Exactly. So on any parameter, you can just right click and then say, set keyframes or whatever, or you say motion effects. And motion effects is basically, if you click, for example, on noise, this will basically create a chop network, which is manipulating directly this context. So this is now overridden by OBG, geo, motion effects, noise, blah, blah, blah. Basically what's happening inside of here. So if I press play now, you can see it behaves very erratically. And this is because it's following that curve. So this parameter is now, noised up by this curve, and the values are just representing that one. Again, it's I hardly use them because I find it a bit hard to control, and you can change the roughness and the exponent, and you can manipulate this curve quite quite on a high level, but yeah, mainly we work with procedural noises rather than chops. So I would rather do this in a VOP context rather than having it in motion effects or in chops. But what's maybe important to mention is that you saw that it created this chop network inside of the geometry context. So currently we are in SOPs. And if I double click here, I'm in motion effects or chops, channel operators, which means that I'm not bound to use these contexts here: channel, image, material, object, out, shop, stage, etc. But these are just, you can work there if you want, but you can also create them everywhere where you want. So I can create shop network. I can create a cop network. And then if I just go in here, then I'm in the compositing context where, you know, I can visualize 2D images, textures, all that kind of stuff. Or even LOPs, so Solaris stuff. You don't have to work inside of the stage context, which is the Solaris context, but you can create it right here in SOPs, and, you know, basically render here and light here and shade here. So it's completely up to you where you do it. Of course, some of the things are better if they're unified, so that if you give your setup to another artist, it kind of makes sense where stuff is. But in general, it's pretty free where you you know, create your context. You don't have to use these guys. Any questions for different contexts? I mean, what happens where? For example, if I do like a pop network, a sphere as an input, and I set the source to scatter onto surfaces, then, you know, it will scatter a bunch of points onto a sphere. If I had gravity, they also fall down. This, again, is a popnet, but a popnet is just a dopnet. So this is where, you know, the naming sometimes is a bit weird, because a dopnet, right, is a popnet. So popnet is like a preset where you create, where you have a pop object, which is a particle object, and a pop source, which is your particle source. But it is both a dynamics context, so it's exactly the same thing. And I can even drop down a popnet pop solver in here, and a pop source, and a pop object, and a pop solver, and everything, because it's just a bit confusing that it's both a DOP network, as it says here. And again, on DOP networks, dynamics networks, operators, it's the sim context where all the sims happen. And as a matter of fact, if you type in solver here, you find like a flip solver, pop solver, pyro solver, RBD solver, whitewater solver, SOP solver, smoke solver. All the solvers live in here. So even like Vellum solvers, they all live in this context. And some of them can work together in tandem, but most of them don't. Except Vellum. Vellum is like a kind of like a multi-solver, because Vellum can do soft bodies, particles, grains, even fluids, since Houdini 19 something. And yeah, just, I mean, we'll talk about all this kind of stuff when we take a look at the setups that I prepared. But in general, it's just, you know, for you to know that all the solvers and the sources are basically living in the dynamics context, or like the .NET. Any questions for contexts inside of Houdini? The kind of like crash course, but cool. Maybe one more thing. So it doesn't, since we are in SOPs here, I can almost like in Nuke, if you look at the name, but if you package a node, you can do the same here. It creates a subnet. If you dive in, you're still in SOPs, and you can, you know, package it up again, and then you're still in SOPs, and then you can package up again, and then you're still in SOPs, and you get it, right? So I have multiple levels of the same context as well, sometimes. So it doesn't always need to be DOPS in SOPs or SOPs in DOPS, but sometimes SOPs and SOPs and SOPs and SOPs, for example, depending on your need. This is an extreme case. Probably you would never do this, but yeah, just to show it. Also, maybe a very handy shortcut to remember inside of Houdini, rather than going like inside and outside of a node, you can press U to go up and Y to go in. So up and in, which is quite handy. Cool. Then let's talk about attributes. So this is basically the basic stuff that I prepared examples for, kind of like how Houdini works at its core. And it, again, resolves mainly about attributes. So we are going to probably cover, looking at the time, maybe not even all of this today. And for the setups that you saw, this is going to be on part 2 for sure. But I would say let's just see how far we get. Cool. So one important thing also that a lot of people struggle with is this thing. So with all these different contexts, sometimes it's a bit tricky to see what's going on in the viewport, because if this is set to hide other objects, you only see this sphere in the current context that I'm currently on, right? If I color the sphere, then I see whatever is highlighted, right? However, when I go to show all objects, I can also see stuff that lives on object level. So if I go up by pressing U, then I suddenly, I see the grid here. I see the other geometry that I created here, which is also a sphere, which I can totally get rid of. Even the cameras and lights are somewhere in the scene, and I can all see them. So for very beginners, it's often super confusing because there's also like this ghost other objects. Then everything on object level gets half transparent, and it's quite annoying. So to be honest, I personally always do hide other objects so that I can concentrate on what I'm working on. However, if I want to see stuff at the same time, and not necessarily merge them together, because I can merge a sphere and a cube together like this, and then I can see them at the same time. However, you don't necessarily want to do this, because this now creates a new object, basically, that has both geometries in there. What you can do is you can set the display flag, that's the blue one, to what you want to see. And there is this template selected. If you click this, you can see this as a ghosted one. If you control click it, you can see it as a solid object. So sometimes, if you're working on a particle sim and there is a character and you want to see the collision, you want to see the character and the particles at the same time, but you don't necessarily want to merge them together, then this comes in very handy that you have this template box. Also, the other, just to finish the other tabs here, lock is you have to control click this, and this is dangerous because lock means it will basically save the geometry in the HIP file. So if you have a very hefty water sim, like I prepped this one. So if you have like this freaking big creature sticking out of don't see the creature anyways, of the water sim, and I would lock this, basically press this, then it would save all the geometry and bake it into the HIP file. which makes the HIP file very, very big, but has the advantage that I don't have to necessarily cache that. However, it's not recommended to do this because, again, it won't be a separate cache file that is referenced inside of Houdini, but the HIP file itself, the Houdini file itself, will become extremely big. So yeah, just a warning basically to use this maybe temporarily to compare a pop sim to another pop sim and then template it and see what changed or what looks better. But I would almost never block this permanently. And then the last one is disable. So you can also press D to can't press D anymore because the shortcut changed. I thought it's still D. Anyways, I'm sure anybody in here knows the shortcut for disabling. Maybe Shift D?
Wait, what? It's not B for bypassing anymore?
B. Thank you.
There you go.
Yes, bypassing. Good. So if you want to disable the current operation you're on, the current SOP, then you can bypass it, which comes in very handy as well. Cool. So let's talk again about attributes and how they're displayed in Houdini. So you do have this sphere, and the sphere, it's important that it's either a polygon or a polygon mesh. There's also like NURBS, which is basically the vector representation of any given geometry. You might know NURBS from modeling, but we mainly use polys inside of Houdini. So it doesn't really matter if you're using polygon mesh or polygon, it kind of does like the same thing. However, what I want to show is that you can, let's say, with this SOP called color, give it a constant color of, I don't know, blue. And if you look now at the geometry spreadsheet, you can see that CDR for red is 0, CDG is 0, and CDB is 1. And that's because this is basically this. If I change this to 0.5, then CDG is also 0.5. And this is a vector, right? This is a RGB vector, and this is a XYZ vector position. And but it doesn't really matter. So what I can also do is say at CD equals at P. If we want to be explicit, we can also do this. And then basically, since it's both a vector, it can be, the position can be also used as a color, or the other way around. The color can be used as a position, and you kind of get it. And if you look at this little, it's a bit hard to see here, this little world axis thingy here at the very bottom, you can see this is basically the reference where X, Y, and Z coordinates are, right? And if you look at the coloring of them, you see that X is red, blue is Z is blue, and Y is green. And this kind of makes sense because if I look at Z, it's blue. If I look at X, it's red. And if I look at Y, it's green. So this is why if PX matches CDR, it basically is like a position pass. If I would render this and give it to a compositor. And that's something, I mean, it sounds very dumb and simple, but it's pretty important to just get that, a vector can be color, can be a velocity vector, can be position, can be basically a lot of things, and it's kind of interchangeable. And they can also be promoted. So if I do like an attribute promote, because this currently we're looking at this attributes and it's all on point level, right? And if I don't want it on point level, but I want it on primitive level, for example, I can easily promote this to primitive. And now you see that basically the attribute disappeared from the points and it appeared on primitive level. And this is kind of hard to do in other DCCs. Especially, this comes in handy when doing simulations and stuff, that you can easily promote one attribute to another class and or another type. And as you see now, the color, since I promoted it from points to primitive, the mode is set to average. So it basically, it has a problem, right? Because the points are gradients. So it's basically from one point to the other. There is a gradient from this, blue color to this more purple color. And once I promote this to primitive level, then it basically takes that average color and promotes it throughout the entire face, throughout the entire primitive in that case. So this is basically a constant color. This is basically a constant color. This is basically a constant color. And I can push this even further by setting it to, I think, detail. So now I have detail attribute and it's set to average again, which equals to black or to this very dark color. So it's not a great example, but what I want to say is, or what I want to show is basically that it's pretty easy to change the class of an attribute to something else. Now it lives on the vertices, for example. And where this comes in handy is most of the time when we get geometry. Actually, this is, I think, this example. Yeah. Most of the time when we get a geometry from another department, it has already normals, right? In this case, I'm just creating normals here. And normals normally live on vertex level. And then we can basically say, no, I want to promote this to points to have the normals from vertices to points. So why do I need this? Because it is cool, because we can use this in a different number of ways. For example, we can color, again, color this based on the position first, and then use the normals to create velocities. So if I set my velocity vector, which basically describes the initial velocities, so that initial force of my of each particle, I can set this to the normals, which look like this. So they're always pointing out, right, perpendicular to each face, and use this as a velocity vector. So my velocities are actually looking like this now. So they're basically 2 times the normal, which, if I make this 1 time the normal, they have the same length, but 2 times the normal, they just have a bit more force. And if I now put this into a pop solver and, get rid of this craziness, then, this comes in very handy because I basically promoted the normals to point level, and then I can use this attribute, which now lives on point level, to drive my point velocities on it, because I need to have velocity on points. I can't have that on vertices when I simulate points. I hope that kind of makes sense. So if I disable this now, and maybe also disable the ground plane here. you can see, this is the pure normals used as velocities. So basically, it's expanding out. Then again, adding back the color. Each point inherits the original color of its origin. So if I change this to dark, see it a bit better. Maybe disabling the grid. Each point, when it gets born, it gets the initial color, and then it basically takes that color and travels with it. If I then, would add like a pop wind, which basically just adds some velocity into the mix, then, you would get this more chaotic thing. If I would then trail this, which basically just, trails it back in time and merges it all together, then I can, create this weird spaghetti thing pretty quickly. But this reaches a bit too far already. So another example, again, would be I can also use normals as my color instead of position. I can also noise up by just, attribute noising up my color, and then setting my position and plussing this by the color. So that means that if I increase the amplitude here, this looks a bit abstract, I have to say, but just so that you get the idea, I'm basically tweaking the amplitude, which is zero-centered, of my color values, right? So the higher this value is, the more extreme the differences between CDR, G, and B are. So right now I'm at from -1 to roughly 1. If I make this very big, I'm at 6 to -4 already. And since I can use, since position is also the color vector is added to the position, it also gets more extreme, the position. So I don't it doesn't really matter if I attribute noise the position itself or first the color, and then use that attribute to drive the position. So yeah, that's one of the principles. Sounds a bit abstract, maybe, but I can also maybe show this here. Yeah, this is basically the prime example of how everything, or like a lot of things that we do in Houdini, are working. And this is very, very basic. So we have a sphere. We transform the sphere. We color the sphere. So we have a red sphere. And here we have, on the original position, a green sphere. And we merge them together. So at the end, we have a green and a red sphere. We can also change this to a torus, right, procedurally. So you change the input, but the behavior, everything that happens downstream is exactly the same. Good. Then, same setup. We have a green sphere and red sphere. And now we do like an attribute transfer and transfer the color, which again is a vector attribute living on point position. We are transferring the color based on a distance threshold and a blend. So if I make this bigger, you can see the gradient gets smoother here as well. If I change the distance, you can see the distance to that other sphere is basically getting smaller. And if we merge them together, again, we have the same as before, but now, depending on where that other sphere is, it transfers its color to the other sphere, right? Pretty basic as well. Good. So now we use this attribute and do an operation on it. So again, we do have an attribute transfer. This time we have a black sphere, which is kind of hard to see, this one, and a red sphere. Again, we transfer the attribute to it, and if we change this, depending on the proximity to the other sphere, it will transfer its attribute. And based on this, we now can scatter points, for example, or like extrude faces or whatever have you. And that is based on that CD attribute. So if I uncheck this, it would basically scatter points everywhere, right? If I check this on, it would only scatter the points based on CD. And since CD is mainly 0, since it's black, it only scatters points where there is the red color, because CD, G, and B are completely empty. And CDR is basically, as you see here, empty here, but it has values here. So if I set the scatter to density attribute CD, it will basically just scatter points where there is color. Cool. So bear with me. This is now the same thing, but animated. So the only thing that I did is this sphere, the red sphere, has two keyframes. So it goes from left to right. And I'm, again, scattering points based on this, right? So the points are basically moving, and it scatters points based on the color again. And this I now can feed into a popnet that we've seen earlier, which basically just takes the input points, and I added some gravity. So now we basically have this kind of very basic effect. And then to take this even further, we tweak the simulation settings based on these attributes. So it's the same exact setup. The sphere gets red over time. Then I'm adding some noise based on the color. So wherever the color gets transferred, if we go inside here, I'm adding a turbulent noise. So turbulent noise basically is just an ambient noise. It needs a position, which is basically the position from the first input, so the position of the sphere. And I also added as an offset the time, so that over time it also wiggles around. I can also just not do this. Then it wouldn't wiggle around, it would be static. And then this noise, I'm basically then, if I disregard this guy, I'm adding this noise to the original position. So taking the original position of the sphere, and I'm adding this new 3D noise, which is basically a vector on each point, and adding this to the sphere. And the result of this, so if I don't add it, it's the original sphere, right? But I'm adding the vector of the noise to the sphere. So that result, I'm then piping into position. If I pipe position into the original position, nothing happens. If I pipe position into the noise, it will be completely broken because the vector of the turbulent noise is now my new position. But if I add this back, it will basically take the original position and add my new turbulent noise onto that position. And what I'm now doing is I'm multiplying that noise by my color. So since my color is here, it's completely black, it's 0. And here it has a value ranging from 0 to 1. So if I multiply this by the color and then pipe that into it, that means that my noise gets only applied in the areas where there's color in the first place. So that basically results in this thing. Good. Then I'm giving it normals. Then I'm setting my point velocities to the normals. So again, we're creating normals based on that displaced geometry, right? So my normals look without this noise, they look like this. as the regular normals from a sphere. If we noise it up, we can see that the normals changed based on the topology and the offset of each point. And now I'm using this normal as my point velocities. So if I now look at my velocities, which are looking like this, and I disable the curl noise here, they match exactly, right? This is my normals, this is my velocities, because I'm saying basically like in the wrangle before, my velocity vector equals my normal vector. The only thing that I did is I also, this point velocity node has this feature built in that you can add on top of that a curl noise. So if I set this to 0, it's the original one. If I increase that, you can break up these velocities a tiny bit. Great. And based on this, I'm now scattering points. And these points inherit the velocities of the objects that they're scattered on. So although I only have not that many points on this geometry, right? It's just like, how many points do we have? 266 points. If I scatter points on here, it will basically, average out the point velocities from each point. And I can have, based on the density scale here, a ton of points, and they have now interesting velocities. And these interesting velocities, again, are based on the normals that are based on a noised up geometry. And I added also like this curl noise. If I don't add the curl noise, then you get straight velocities from the displaced normals, basically. Cool. So this way you can basically sculpt your velocity vectors type it. And then the next operation is basically giving it funky colors. And I did the same as before. I set my color to the position. So it's basically equaling what we did before, where we set at CD equals at P. So this way you can create like a gradient. However, what I did is I changed the range, not from 0 to 1, but from 0 to $t. $t is basically time. So over time, this changes. After 1 second, so 24 seconds, this will be 1, like so. And then after 2 seconds, it will be 2, etc. So that's $t is just a variable for time. You can also say frame, $f, for example, but then it would be much faster because each frame evolves faster than seconds. And then last thing I did is I set ramp from attribute to basically remap the colors to this ramp. So, and everything together, like the tweaked velocities, the color based on the ramped position attribute, with the range changing over time as well, is equaling into this very abstract source that kind of looks funky. And if I now use this very funky looking abstract source in a popnet, then I get this weird looking fluid magical effect maybe, which it's not very helpful in any ways, but it's a good example, I think, for using attributes to create interesting looking stuff. And this can be taken then even further. So if I use these points, this is a DOP import. So basically what this does is basically just it imports data from a dynamics context. And my dynamics context is this one. And there's this pop object. So this is basically the objects where all the points are in. So basically I'm just saying I want from my popnet, this guy, I want pop whatever, pop star, because the only thing that is called pop something is this pop object. So I can also, copy this and say pop object. It will result in the same thing. This wildcard thingy is just handy to get it quicker in. So I have the points from the simulation, and I have the grid, which has a couple of. So this is quite high res, the grid. If I make this grid black and use the colors of these points falling down onto the grid, and do the same thing again, I'm transferring my attributes from the points that are falling onto the grid. Then, based again on the distance threshold and the blend width, I can again do the same thing as with the two spheres. I have to pop out. That was a good one. I have to remember that one. Actually, we are at the end of the time. It's 5 p.m. already. I would just wrap up this section, and then if there's questions, we can have a little Q&A, and then next stuff, all the other stuff, including all this plus the setups, we can cover in part 2. So I'm just going to hurry. Again, this is the grid, which you currently can't see because it's black on black, so it's not very helpful, but we transfer the colors from the points onto the grid again. And then based on this, we're doing the exact same trick as before. We're using a turbulent noise, we're multiplying this by the color and adding this to the position, which basically equals to a displaced ground. And if I then, kill everything where the color is 0, so a blast node is basically a prune or a delete node, and I can dynamically group this by saying add CD, so where my attribute color equals 0, so where my color is black, just delete everything. So it basically deletes, everything where the grid is black. And then I give it normals. So this way I can reveal the underlying grid based on the proximity of the falling particles, which, I don't know, would be kind of like cheap infection mask, something, that grows over time, that reveals another character or whatever have you. But this, is basically not everything that we are doing, but a lot of what Houdini is about attributes, using these attributes to drive something that again drives something else, and then based on this, create velocities, forces, parameters that drive simulations that then look kind of interesting. And I hope this kind of makes sense. If not, I'm very sorry. Next time, we're going to talk about all the other stuff like for loops, SOPs training, and solvers. Actually, this part, I'm very sorry that we didn't get to what's a simulation and what's a solver, because it's quite dumb in what it's doing, but it's also quite interesting. So yeah, next time we'll talk about all that stuff, and thank you for listening. If there is any questions, please shoot. And I'm stopping the recording.